Hello, everybody. That was the best noise I could find for a laboratory. Okay, we are going to be talking about something a little bit different, but is still about modeling with systems. So I'm here in my lab setup because we're going to be talking about some physics stuff. Okay, and specifically what we're going to be talking about is the mass spring system. Okay, now this is something that we have discussed and derived before when we were doing second order differential equations. And what's nice about invoking it here is it does a couple of jobs for us. First, we're going to see how you can go from a second order differential equation to a two-dimensional first order system of differential equations, and it's an example in physics. Okay, so if we are modeling here, let's say a mass and spring, so we get a little mass on the end of a spring where there's no friction for now, so all you got is the spring restoring force and no outside forces. So we've got nothing in terms of x prime, there's no f of t, and we just get that k over m, that spring restoring force and the weight of the mass at the end. Okay, to make some of our math a little easier, we are going to make a couple of simplifications, but to start off with, let's say v, which is the velocity of the object, equals x prime. Then v prime is x double prime, which is the same as negative k over mx. And so we wind up with actually this rather nice looking first order system. As opposed to a second order differential equation, we've just got x prime equals v and v prime equals negative k over mx. Let's make the arithmetic simple. Let's go ahead and let k over m equal 1 just because I want to. Otherwise, we're just going to have some terms we're carrying around. It doesn't change any of the fundamental results. All right, and so what this does to our differential equations in the end is we've just got x prime equals v and v prime equals x. So we can see how that interaction there, x is influencing v's value and v's value is influencing x's value. Okay, I want to think of that again as a vector field or a vector valued function f on x and v, which equals v and negative x. Now, if we think really hard back to multivariate calculus, okay, this was a prototypical example, okay? If I look at my second order differential equation, it's a little hidden there, but if I look at the system of differential equations, take a function x and its derivative will be v. Now take the derivative of that function and you get negative the first function you start with. That's classically differential equations. And so cosine of t and negative sine t will fit the bill here on this thing. And this is what we understand. We remember this from second order differential equations, yada, yada, yada. But what I'd like to is to continue thinking about things on a phase plane instead of necessarily just time series. Okay, so I've got x here, I've got v there, and this is my vector valued function. We take a point, I'm going to take a point on the x-axis. So v equals 0, which means I have no horizontal change. All I have is a downward vertical change because my downward direction is described by negative x and x is a positive value. If I take a value, let's say on the negative part of the vertical, I get pure left. On the left part of the horizontal, pure up. And on the top part, pure to the right. And again, this is just through here, and you could choose any other values there, and you get something that kind of looks like a circle, but we have to remember this is not perfect. We're not doing each individual point, so we don't know if this is actually trying to spiral outward, if it's trying to spiral inward, or if we actually are on some form of closed orbit where we will go around in a circle. Okay, this is actually easily verified here in this case because we know that cosine of t and negative sine of t are my solutions here to this differential equation system. So I actually know since since x squared plus v squared equals 1, that's exactly how you parameterize a circle, so it will stay on the circle. Okay, just a really quick and short video here to kind of show an example that's not biology, although for the interacting systems in general, that's probably where I'm going to go most often. All right, thank you guys. And I hope this made sense, and I'll catch you later. Okay? What does that say? Get pure oscillations. Yeah, we know. We saw that. All right. Bye-bye. Where's my stop button? There it is.